it going, everyone? Mr. Geyser here with the video for our Lesson 7B on sinusoidal functions using that context and data modeling. Let's continue our investigation of real-world applications related to these sinusoidal functions. In example 7, alternating current is the form in which electrical power is delivered to most businesses and residences. And it is the form of electrical power consumers typically use when they plug televisions, lights, and any electrical appliances into a wall socket. The current I in amperes flows through an alternating current at t time in seconds is modeled by this equation here, where t is always greater than 0. In part A, we want to try and find the amplitude, period, and phase shift. And I already know all of you guys can identify that 220 volts here as the amplitude for this function. We now can grab this b value of 60 times pi, and we can use that in our period equation, where we take 2 pi divided by 60 pi and find that a period length is about 1/30. That final piece is going to be our phase shift of negative 1/360, where we can articulate that this is going to be a phase shift to the right-hand side towards me, 1/360. In part B, we now want to try and graph 2 periods of this function. To do that, we want to try and find the start and the end point of both of these periods. First, we grab that c value as our start point for our first period, and we're able to simply add our period length to that c value to find that second point, or that first end point for that first period. And again, start point c, end point is c plus p. Now we'll do that one more time, where we're going from now this as our start point, where we add 1/30 one more time to get this second endpoint. Once we have those 3 x values, we're able to plot that onto our graph. Quick little important detail is that our d value is equal to 0, so our midline is still going to be on that x-axis. That first point there is still going to be c. That second point there is just going to be c plus b. That third point here is just c plus 2p. And we're able to find the next endpoint for that next period by simply multiplying p by that number of periods we want to try and find, and then adding that to our c. Once we have these 3 points, we're able to find this middle intersection point between each of these periods. The reason why we know that there is a third intersection between this period here is because it follows those 5 key points of a sine wave. Those next 2 key points are going to be the maximum amounts and these minimum amounts for both of our periods. Once we find all of these points here, we're now able to simply graph our points together. One important key detail is that these maxes and these mins always fall right in between both of these intercepts for that period. We now can create this connected point here, where we're now graphing out this sine graph. In part C, we want to try and find where the x-intercepts of the function are, those 3 little key points for that sine function. What do they represent in context to the current? Well, we're able to find that first point there by simply grabbing that phase shift, and that second point there isn't simply going to be that phase shift plus the period, because there's going to be a hidden intercept halfway between the period. So to find the intercepts, we just take c plus half the period to find it occurs at 4/360. That next point, or any equation to find all of those points for that intercept, is just going to be that n value, where n is the number of intercepts you want to try and find, and you're multiplying it by that p/2. In context to this problem here, these intercepts are where the function crosses the x-axis, or where the current changes direction from positive to negative. Move on to example 8, where Cheryl opened a bakery and found that her monthly profit followed an up and down pattern during the first year. She discovered that her profit could be modeled by that p of t equation, where p is measured in hundreds of dollars and t is measured in months after January 1st. We want to try and use a graphing utility, our TI-84 calculators, to try and answer these 2 following questions. First, when did the bakery begin to make money? Explain how you know this. First thing we want to try and do is bring this equation here into our TI-84 calculators. All I've done is grab this TI-84 calculator, hit that y equals, and plugged in our equation that was given to us. The second thing that I've changed, just to flow a little easier, is I've changed the window in which I'm viewing this equation. I'm going from that minimum value of 0, that max for x value is 25. The minimum value for y, I made negative 10, and the maximum value for y, I made 60. That way we're able to see this graph here slowly increasing over time, almost as if this sine wave is almost increasing in a linear fashion. In part A, we want to identify where this bakery started making money. Really, it's just when the graph is now in that positive it's in that positive area. To find that, we need to identify what that 0 is on our graph. To do this, we want to use the calc function on that F4 key. We're going to hit our second option here, calc right above trace, and we want to use that 0 calculation on our calculator. We go down to that second option for 0, and it's going to ask us to identify a left bound and a right bound. That left bound needs to be on that left-hand side, the left-hand side of that 0, while the right bound needs to be on the right-hand side of that 0. You basically slide your little cursor all the way down until you reach the left-hand side, or the negative section of this graph. Hitting enter, and you know you've done it right when you have that straight line appear on your display, and there's a little arrow at the very top of the graph pointing towards the right-hand side from the left-hand side. I'm now going to go over to this right-hand side, hit enter, and a second line appears pointing towards the left-hand side from the right. We now have this window where the calculator is going to calculate where 0 is, and that last point we need to do is our guess, right around where we think 0 is going to occur. And for us, 0 occurs at 2.311. Now, what does it mean that it happens at 2.311? We want to describe that the bakery first begins to make money sometime in March because the graph becomes positive at 2.311. And that's going to be sometime in March, about a third of the way in. Now, in part B, we want to try and find what month did her shop make the greatest profit in the first year only. What was that profit? We can go back to our graph here, and we're going to use a brand new function for the maximum value of this graph. We want to hit this second option here, and then go back to calc, and now go down to that maximum value. For that maximum value there, we want to make sure that our left bound point is all the way at 0, because that's when she first started doing her bakery. Hitting enter. And now we want to go over 12 units for a full year, because that was the 12 months are in 1 year. There we go. Now, that last third point is always going to be a guess. And I can see that our cursor is pretty close to that first little that second little maximum there. When I hit my guess, we can see that that maximum occurs at 10.763. Once we bring that back into, I apologize. The x is 10.76, but the y value is going to be 28.26. We want to do something with that 28.26. For part B, we can state that in November, 10 point something, the bakery hits its maximum at 10.75, about 3/4 of the way in, at 28.26. This means that the bakery made $2,826 of profit in the month of November because our values are in hundreds of dollars. Now, in example 9, hurricanes are categorized using the Saffir-Simpson hurricane scale. The table below represents the number of major hurricanes in the Atlantic Basin that have been rated as a major storm of category 3, 4, or 5 for each decade between 1921 and 2020. We're going to use a graphing utility to create a scatter plot of the data for t equals 0 to t equals 10 for the decades shown in the table below, where that first decade between 1921 to 1930 will be our x value as 1, that next decade will be our x value 2, and so on and so forth until our final decade is x equals 10. With that information, we want to try and transfer that over into our TI-84 calculators. The most important button that we're going to use for this equation here, and most of our problems in pre-calculus, is going to be that stat button. We're going to click on the stat here, and we want to immediately go to edit. Once we click on the edit, that L1 column is where we can bring in that 1 through 10 x value, and that L2 column is where we can bring in that 5 through 9 y values for our problem. Once we bring in those values there, we're able to see our scatter plot on our grid here, and it looks relatively like a sine wave, or a cosine wave here, where we can try and showcase that this might be a type of sinusoidal regression model, where in part B, we want to try and find a sinusoidal regression function to best fit and model the data. To do this, we're going to go back to our TI-84 calculators. I'm going to go ahead and hit second and quit. Just brings me back to that home screen. And we're going to go right back to that stat button there. But this time, we're going to tab over to calculate. And then we're going to go, for me, up, because it brings us to the bottom of the graph. And we want to go to that sine regression model. For this sine regression, our first option is the number of iterations we want to do to this regression model to get as accurate as possible. It's set default to 3, but the general number that's suggested to us to use is 15. The more amount of iterations you do, the more accurate it's going to be, but it's going to take significantly longer for your calculator to calculate. For our x value list, it's going to be that L1. Our y value list is L2. It's already set up that way. The last thing we need to change is where we're going to store this regression equation. We're going to tab down to that store regression equation, and we're going to select the variable options and then tab over to y variables. I want to bring that function into our y functions here, and I'm going to bring it in to that y1 function. Once I do that, I tab down to calculate, and once I hit enter here, I'm given my a, b, c, and d value. However, what I want you guys to spot and notice is that the form in which our TI-84s have our sinusoidal regression is not the general form for harmonic functions. What I mean to say is, notice how that b value is simply multiplying x, and c is in the parentheses. They're not separated together. So this is not the same kind of format that we're normally used to. For these regression models, we stick with this kind of format where we have our a in the same place, our b right in front of our x, and this is no longer our c value, where our d value is still at the end. We are still able to find what our c value is in problems like this. I'm going to pause here and say that this here is the answer for b. I want to go on a side small tangent where, if you are given problems like this theoretically, and you want to try and find your c value, all you really want to do with problems like this is to try and undistribute that coefficient, where really you just take this argument here of 0.9x minus 1.4, and you're dividing that coefficient from both of those terms. You're then able to pull out that coefficient from x and this coefficient from that constant here to find our c value. Now again, this was just a side example. Our answer for the regression model for part B is this top equation. Now we want to look at part C, where in part C, what is the maximum and minimum number of storms based on your model? Well, let's go check it out on our graph. We go over to our graph here. We now have that scatter plot and this y equals graph for us to plot onto our graph here. And we can kind of see how close our regression model gets compared to our data set. But we want to find that maximum and that minimum value of our regression model. To do this, we're going to hit our second option, go back to calculate, and go down to that maximum value here. And in our case, we have two maximum values to choose from. They should both be exactly the same maximums. I'm going to choose this second maximum over here. I'm going to tab over just a little bit to the right. And then I'm going to hit enter for my first left bound point, tabbing up over that maximum for my second right bound point. And I'm going to make my guess at the very, very peak of this wave here. And we can find that the maximum value is going to be that 9.56. And we can do the exact same thing with the minimum function. Same idea. We're just going to hit second, calculate, and we do the same exact process for the minimum value at those bottom troughs. We can bring this into here and say that that maximum value occurs at 9.7 or right around 10 storms. And the minimum value is about 3.6 or right around 4 storms. In part D, in which decade will the next maximum number of storms occur based on the model? If we look back at our model here, we want to try and find where this next peak is going to happen. That last peak was 2 decades ago. What we want to try and do is shift the graph 1 full period length over to find where that next maximum occurs. To do this, I'm simply going to go and open my window. And for my x minimum here, I'm just going to move the whole graph a year forward. So I'm going to type in 12. Or sorry, I'm going to type in 10 here, the next set of 10. Not a whole year forward, I apologize, a whole century forward. So I'm going 10 forward, starting that next part of the decades. And my x maximum, I'm going to make 22, a full century ahead. I'm going to keep my y values all the same. And now we're able to see our new maximum. Our new maximum here, we simply grab that second, go to calculate, go down to maximum, and we want to try and find exactly where that occurs. And this should occur at 15.98. But what does that 15.98 mean in context for our x value? Well, theoretically, according to the regression model, the next maximum should occur at 15.9.7. This means that this should happen between 2071 and 2080 is when we'll have another large spikes of these category 3 through 5 hurricanes. Now, in example 10, we're going to work through together a sample-free response question. The table below shows the average temperature per month for Atlantic Georgia. The information can be found using this World Climate website above. The table shows months from January to December and the average temperatures for each of the months. In part A, we're going to plot the data to the right side here and notice if this data is approximate towards a sinusoidal behavior. Our first step is to change all of these months here, not to months, but to numbers. We want to make them going from 1 to 12. That way we can plot these on to our graph here, where we kind of start pretty low. January is pretty cold. And we start heading up, where in the middle, right around July, is when it's the hottest, all the way back down in December, where it starts getting colder. We now can plot these points here, connecting all these dots now. And now for part A, why does it make sense that the average monthly temperature can be modeled as a periodic function? Well, we know intuitively that seasons go through and follow a cycle throughout a year. Ideally, the average monthly temperature between years shouldn't change drastically. We now want to try and take a look at part C. In part C, let's model this graph with a sine function in the form of y equals a times sine in our general form that we know. We're going to use the data to plot, we want to use the data plot to estimate the amplitude, the period, the phase shift, and the vertical translation. First, let's just grab that amplitude value here, where that amplitude value is just going to be this maximum amount and this minimum amount. We're going to take the difference between the maximum and the minimum and then divide by 2. We find that the amplitude here is 18.35, and we're actually going to skip part B and C and go right to that variable of D. The reason why is it's relatively the same type of equation as our amplitude. Our midline function is just going to be our maximum plus our minimum divided by 2, where that midline occurs at 69.95. We now want to try and grab our B value here. We don't quite know what the B value is, but we know the period is going to be a full 12 months because it's 1 year. Since we know that period and B are interchangeable, and since P is going to be 12 because there's 12 months instead of a year, we plug 12 in the denominator. So 12 or 2 pi divided by 12 becomes B is pi over 6. And now for C, C is a bit difficult. I'm not exactly sure how to find that value there. I do know that our value is going to equal that 69.95, but it's a bit difficult to try and find what our C value is with this equation. And in general, we kind of have this so far, where our A, our B, and our D are replaced, but we still have these 3 unknown variables, that Y, that X, and that C. And if you ever have one equation with multiple unknown variables, you cannot solve it. But if we plug in one of these values, minimum, maximum, one of these intercepts here, that we know to be true, we're now replacing this Y value, which was unknown, this X value, which was unknown, and now we have one unknown for one equation, which means we're able to solve this equation. To do that, we take 2 pretty fast, easy steps. We're going to subtract that 69.9 and then eventually divide that 18.35. These 2 steps here, Very easy algebra, just add or subtracting that to both sides, dividing this to both sides, to end up with this equation. Now I want you to think in your heads, when is sine equal to -1? Regardless of what this argument is, when is sine equal to -1? Well, if I bring up our unit circle, I can see that sine occurs at -1 at 3 pi over 2. And I can say that sine of 3 pi over 2 is equal to -1. And -1 is equal to that function there. Well, there's no point in having that -1 anymore because they're going to be equal to each other. Well, there's no point in having the sines anymore because this argument, 3 pi over 2, should be equivalent to this argument, pi over 6 times 1 plus c. We now set those two arguments equal to each other, and it's going to be this that we're going to solve for. That very first step when it comes to solving this out is simply multiplying by the reciprocal b value. This happens to be frequency. It's not really relevant for this problem. When we multiply by that reciprocal, that b value simplifies out, and we end up getting 9 on that left-hand side. Now we just subtract 1, and we get our c value is now equal to 8. 8? What do you mean? That's a positive 8. We have this phase shift going to the right-hand side. So we should have like a negative value of some kind. Well, if we actually extend this graph the other direction, I can see that our phase shift actually is 8 units. It got shifted back 8 units this way. Well, actually, I know that if it's getting shifted back 8 units and my period is 12 units here, another way we can describe our c value is with this phase shift of -4. Notice that we can describe this function as a phase shift of +8 or of -4. Really, all this is the difference between one period. Now that we've captured this equation here with that a, b, and c value, let's try and have our TI-84 calculators take care of this with that regression model. For that regression model, we're simply adding all of those data points back into our TI-84 to eventually get this regression model here. I'd love for you guys to try and practice trying to get this regression model. Now, in part E, we want to try and explain the meaning of the points of inflection in context of the data. Remember, those points of inflection for sinusoidal graphs are always the intercepts across that midline. For those intercepts across the midline, that first one occurs right around 3.7. So in late March, the average monthly temperature increases at a decreasing rate. So right around the end of March, like right around now, we should start feeling that the temperature is increasing, but it's slowly increasing slower and slower. It is going to get pretty hot soon. However, in early October, the average monthly temperature starts to decrease at an increasing rate, where we're now getting colder, though, at a slower rate until it gets to that maximum coldness sometime in January. We want to take a look at this final problem here for part E. We want to explain the meaning of the maximum and the minimum values of that regression model as they relate to the context of this data. That maximum and that minimum value for our regression models are going to be unknown. I'm curious to see if you are able to find what these y values are, the temperatures of that maximum and that minimum for our regression model. To find that context sentence to describe it is meaning in what month are you describing the yearly max temperature reaches blank. Meaning what month the yearly minimum temperature reaches blank. Your goal here is to try and find these max and minimum values for our regression model. Thank you very much for joining me on our Lesson 7B, where we looked at these real-world problems, a few physics, a few chemistry, and for us to try and analyze them in terms of our sinusoidal functions. Thank you very much for joining me. If you have any questions, please leave them in the comments down below, and I look forward to seeing you guys in class. Take care.